So we've talked about index refraction and how the light bends as it goes from one medium to the other. And so we've looked at, N1, N2 condition. What we've done so far is N1 less than N2. And so if you draw a perpendicular to the surface, then light comes in here, and then it bends at an angle like that. Okay. And so the theta 2 is going to be less than theta 1. But what if we had a situation N1, N2, in which N1 was greater than N2? Then what happens is, then this would be theta 1, but now what's going to happen is theta 2 is going to be a bigger angle. And so you keep looking at this, and as theta 1 gets bigger, theta 2 gets bigger, but then you realize that you run into a problem. At some particular theta 1, theta 2 is going to equal 90 degrees. And so the question, what happens after that? So after that, so it's like N1, you got N2, we're assuming that N1 is greater than N2. Okay, so draw a perpendicular here. For small theta 1, then theta 2 is bigger. For a critical angle right here, theta 1, theta 2 is 90 degrees. And for a bigger angle than that, theta 2 be bigger than 90 degrees. We can't really refract bigger than 90 degrees. So what happens is you get reflection. And so the angle of reflection is going to equal the angle of incidence. And so the question is, okay, so if you try to get an angle there that is steeper relative to the perpendicular, in other words, it's more shallow relative to the surface, then you're going to get reflection. And you've seen this effect. You've seen the effect now and then. For example, on a road, in the hot summer day, you get a layer of air. The warmer air here is actually going to have a different index refraction than above, and so light will come in here, and if the light is at too steep of an angle here, it's going to reflect right there. And so when you look here, you're going to look this way and see the sky over there reflecting off of the road down here. Or off of water, you can see the same thing there too. So you can see this sort of reflection there, and again, it sometimes happens if you have a layer of air right there that's got a different index of refraction because it's a different temperature. Now we haven't really talked about how that works. That's a little more complicated topic there. But it turns out there's another way you get reflection there too, off of a surface. We'll get to there. We will get to that. Okay, so let's get back to this critical case. So the critical case, N1, N2, okay, in which this angle right there, the critical angle, is such that the refraction here is 90 degrees. Okay, if we have an angle bigger than that, we will get reflection. Okay, an angle less than that will refract. So, well, we know that N1 sine theta c equals N2 sine 90 degrees. Well, so that means sine theta c equals N2 over N1, because sine of 90 degrees is 1. So theta c, the critical angle, is the arc sine of inverse sine of N2 over N1. Okay, and so that is the critical angle for total internal reflection. Okay, so now let's do a couple of examples using this. So let's consider water. So N is 1.33, and then air is above the water. And so we've got a fish here. Okay, and the fish is some depth h, and let's say that h is going to be 1.25 meters below the surface. And so as the fish looks straight up, see here, if the fish looks an angle there, then they see something off this way. If the fish looks like there, then it goes straight this way. And the fish looks off this way, then they see like another fish over here somewhere. Okay. And so that means that the fish sees all that's on the outside of the world focused into a little circle right here, a window. In fact, we sometimes call that Snell's window. So I want to know, what is the diameter of Snell's window there? Okay. Let's clean up my picture a little bit. So we have water below, air above. Okay. So we've got the fish down here, some height h. Okay, here's the critical angle. Okay, now the critical angle is really defined right there, but that's going to be the same as this angle right here. Okay, so if we can find the critical angle, then we can find r. And then we know that d is going to be 2r. Okay, so the critical angle is going to be inverse sine of 1 over 1.33. So the critical angle turns out to be 48.8 degrees. Well, we look at our diagram over here, and we see the tangent of the critical angle is going to be r over h. Okay, so r is h tangent of the critical angle. So that's going to be equal to 1.25 meters times the tangent of 48.8 degrees. And that comes out to be 1.43 meters. The diameter of Snell's window is twice that, so that's going to be 2.86 meters. So this is an example here of total internal reflection. There's a couple other places we see total internal reflection. Another place we often see total internal reflection would be if we had a fiber of some sort here, a glass or plastic fiber, acrylic fiber, and so what it can happen is that when light comes in here, hits there, total internal reflection, total internal reflection, total internal reflection, total internal reflection, total internal, total, and then comes out the other end. So the light continues going through the fiber, bouncing off the different walls until it comes out. Well, that's obviously how a fiber optic works. And so fiber optic gives you this ability to have light directed around corners or wherever you want it to go. So this is the idea of a fiber optic. That's the basic concept right there. Another place you see total